Good afternoon, ladies and gentlemen. My name is Mozgovoy. I'm a PhD student in University of Lausanne, Swiss Graduate School of Public Administration. Please feel free to ask your questions in the end of the presentation. The topic of my today's talks is stress pattern recognition through wearable biosensors in the workplace. This is experimental longitudinal study on the role of motion intensity. Today we will discuss how machine learning methods can help to induce stress-related states by combining physiological and non-physiological data. But at first, I would like to give you a background information about stress and also about wearables. Then we will see what machine learning methods exist in this area of research, and I will show you the application of some of them related to concrete research problems and specific data. Finally, we will discuss findings and implications. So what is stress and why this problem is important? Stress is defined as relationship between individual and environment that individual perceives as taxing or exceeding individual's ability to cope. And stressors can be both physical and mental. Excessive stress can lead to the development of diseases and to the mental and physical dysfunctions. Also, stress is a burning issue in public service organizations, and research evidence shows that this problem will continue to grow. However, modern information technologies coupled with machine learning methods can help to early identify stress and possibly prevent it. What we understand by wearable devices. Wearables are computational body-worn devices that sense individual and individual's environment. They also facilitate the data collection in the dynamic settings. User typically interacts with wearable devices that collect some data on user and send it to remote processing unit. And this unit transforms this data into some visualization or quantified feedback and sends back to user. Here are some examples of wearables. They are very often coupled with smartphone or tablet that help to display visualization. On the left-hand side, you can see smartwatch that is suitable for daily life use. On the right-hand side, in the top, you see smart sleep that is suitable for training. And here above, this is armband with sensor that is suitable for office setting and also for hospital setting. Concerning the machine learning methods that exist in this domain, their choice depends on two major factors. The first is a type of environment that can be restricted as laboratory environment, which favors a supervised learning approach, and open environment like daily life that favors unsupervised learning. And also type of monitoring matters, because self-monitoring it assumes that user knows a lot of contextual information and it requires less physiological data. But remote stress monitoring will require more variables to take into account into our model. Next, this study is focused on the remote stress monitoring context. And the aim of the study is to explore whether by adding additional non-physiological signal we can improve stress pattern recognition and we can gain some additional insights about stress-related states of individual. In theory, non-physiological signal shall provide us with additional contextual information about users' activity, help to control for the confounders, and help to better distinguish between various stress-related states. About experimental setting. This experiment was held in Swiss fiscal administration, and it involved 18 participants. They weighed the devices during 2 months, around 2 months, and principally in the workplace. It is a group of locations where people could move around during their working hours. And those devices registered physiological and non-physiological data that later was used for stress pattern recognition. So, concerning the methodology of current study, it doesn't exist a well-established methodology for remote stress pattern recognition in the workplace context. However, we know that this type of environment corresponds to semi-restricted or open environment. Thus, we favor unsupervised learning. On another hand, this is remote stress monitoring, so we would like to include additional contextual information related to users' activity. And given that, we follow the next steps to address our research problem. So we consider physiological and non-physiological signals. We perform clustering analysis, and we interpret clusters with our theoretic knowledge on stress. Finally, we evaluate uncertainty with bootstrapped confidence intervals. Concerning physiological and non-physiological signals, what we consider. At first, heart rate. This is a common measure in stress-related studies. Research evidence shows that heart rate may increase during episodes of stress. Another one is galvanic skin response. It reflects the emotional arousal, and research evidence shows that it may also increase during the episodes of stress. And finally, the non-physiological signal is motion activity that reflects motion intensity. This is very interesting signal because at one hand side, one of the factors generating stress has physical nature, but at another hand side, an increase of motion intensity or physical activity does not necessarily lead to stress. So this is a very interesting contextual variable to take into account. The algorithms used in this work are K-means and Gaussian mixture model. The first one corresponds to hard clustering assignment, and it doesn't assume any distribution for the component. However, Gaussian mixture model is a soft assignment algorithm, and it assumes Gaussian distribution for mixture components. Also, it adopts a probabilistic perspective. And now let us see what we know from the theory about the major stress-related states. So according to the Yates-Dodson law of arousal and catastrophe theory of arousal, there exists a low range of arousal, middle range of arousal, and high range of arousal. Middle range of arousal and high range of arousal can be associated with various degrees of physical activity. Low range of arousal by itself is not dangerous for individual well-being. However, if the state is experienced over a long period of time, it can lead to boredom, inertia, and lack of motivation, sometimes even to stress. The optimum condition for individual is the middle range of arousal. At this point, individual perceives the maximum motivation and maximum productivity. Also, it may experience some mild symptoms of stress. However, they are perceived rather as thrilling and exciting. At another hand side, middle range arousal can precede the over-arousal state. At this point, when over-arousal is perceived, this state is highly likely linked to the stress. And now we want to explore the structure of our data, and we want to identify three major classes from the data. After that, we want to analyze the centroids of clusters, and we want to analyze the activation of each component. Then we want to find the correspondence between our analysis and theoretic knowledge on stress using Yates-Dodson law and catastrophe theory of arousal. And finally, we suggest the analytic labeling of the classes. So let us look more into details on those classes. At first, red cluster is labeled as our over-arousal. We can see here that galvanic skin response, reflecting the emotional arousal, has the highest activation among all other clusters. At the same time, heart rate has highest activation as well. Finally, we conclude that this cluster has highest relationship to stress than blue and green cluster. Let us see more into details green cluster. At first, green cluster corresponds to the medium activation of galvanic skin response in respect to all other states. According to the Yates-Dodson law of arousal, this is the medium range of arousal that corresponds to the highest productivity of individual. However, this state may also precede the state of stress, thus it is very interesting from the point of view of stress monitoring and stress prevention. At the same time, we can see that increase of motion activity is associated with increase of heart rate, which represents the natural reaction of a human body to increase of physical activity. Finally, we conclude that green cluster has less connection to stress than red cluster, and it is analytically labeled as arousal cluster. Interestingly, in current work environment, we haven't observed cluster with high activation of emotional arousal and motion activity at the same time. And according to the catastrophe theory, it would correspond to the class where humans' energy drills very fast and stress occurs very fast. And finally, let us see blue cluster. It corresponds to the lowest activation of motion activity, heart rate, and galvanic skin response, and correspondingly it was labeled as the class of relaxation. Next, we can continue our analysis with the Gaussian mixture model and look more into details on the emotional arousal components. And according to the theory, we know that there is low range, middle range, and high range of arousal, and high range of arousal will be more related to stress than any other component. So let us sum up what we have seen so far. There are distinguishable stress-related patterns that characterize specific work environment, and we can analyze those patterns with help of wearable devices. And it is also possible to build unsupervised classifier with the help of algorithms and theoretic knowledge about stress. And motion intensity is additional variable that can help us to get additional insights related to stress and improve our stress pattern recognition. And by implication, we can design stress monitoring programs that will consider both daily life and workplace environments, because people often bring stress, work stress to home and home stress to work, and they are interdependent. And also this study may contribute to the development of new processes, practices and procedures of stress monitoring. Also, this study gives a road for the future research. For example, it may be important to validate the analytical labeling of these classes with help of questionnaires, that is psychological measures of stress. Development of stress-related anomaly detection systems is possible. Using the cluster labelings, we can also develop meaningful indicators of stress-related states on individual and also on collective level. Then we can develop methodologies that incorporate physiological measures, non-physiological measures, and psychological measures. Also, unsupervised learning problem can be used in order to characterize specific work environments, to understand what are the clusters, what are the respective weights of the clusters, and potential vulnerabilities of certain work environments. Then we can compare some environments between each other, and so forth. Thank you very much for your attention, and please ask your questions.